What's up, guys? Welcome back to a brand new YouTube video, and today we're going to be talking about analytic trigonometry. Now, within analytic trigonometry, there's basically two main big ideas, and that's going to be solving equations using trigonometric equations, and second is going to be verifying trigonometric identities. So first, let's talk about what trigonometry is. So trigonometry is just going to be the use of our sine theta, cosine of theta, and tan of theta. So now quick review, if we have a right triangle like this, and this is our theta. This is going to be the opposite side. This is the adjacent side, and this is the hypotenuse. Sine is just opposite over hypotenuse. Cos is just adjacent over hypotenuse, and tan is just opposite over adjacent. So now we have these functions. That's super cool. But the thing is, and we also know a couple values, right? For example, we know that sine of 0 equals 0, sine 30 equals 1/2, sine 45 equals root 2 over 2, sine 60 equals root 3 over 2, and finally sine 90 equals 1. Okay, so that's super cool. We can, given like a theta, we can find the ratio using our trigonometric functions. But say instead I had something like this. Say I had sine of theta equals 1/2. How in the world am I supposed to find theta's value? Well, if we come right back up here, we can see that when sine of anything is equal to 1/2, then theta is 30 degrees, as we see right here. So from here, we could deduce that theta equals 30 degrees. But say we had something else. Say we had something that wasn't in one of our like main numbers. How would we solve that then? In this case, we're going to have to use an inverse function. Now, when you hear inverse function, what do you think of? An inverse function is basically something that undoes another function. So say we have y equals x squared. If I were to find the inverse of this, we just switch around the x and the y, so x equals y squared, and then solve for the y, which implies that y equals the square root of x. Now let's do something interesting. Let's say, instead of calling this y, this is f of x, and since this is the inverse, I'll show you why in a reason, we'll call this f inverse of x. And we show the inverse with a -1 up at the top. Okay, so now let's take f of f inverse of x. So this is just going to be, we know f of x is, or first let's do the inverse. We know the inverse is root x, and we're going to do, so that's the inverse right here. And we're going to do the f of x now on it. We're going to square that entire thing. What do we get back? Well, the square root of x squared is just going to be x. So you notice we get the x back. From here, we can probably deduce what the inverse of sine is. Sine inverse looks like this. Sine inverse of sine theta. And guess what we're going to get back? We're going to get back theta. So this sine inverse undoes the sine in here. Now, I know this does look uncomfortably like to the power of -1, because when we do like sine squared, we write it like this, but this is not sine to the -1. When you see an inverse like this, it's going to be equal to arc sine. This is another word for the inverse of sine. And in order to avoid this kind of confusion, anytime we actually have sine to the power of -1, we're just going to do 1 over sine. Okay, so now we're in Desmos here, and now that we know what the inverse trigonometric functions are, let's talk about what they look like. So we know that sine of x just looks like this, right? So if we were to take the inverse of this, what did I say we do? We reverse the x and the y. So if normally it's y equals sine x, now we're going to do x equals sine y. So now you see that we've kind of like, inverted it. We've kind of flipped it over the line x equals y, and that's another way to find the inverse function. But anyways, what do you notice about this? Well, let's go back to our definition of a function. A function is something that has like a one-to-one ratio, right? Or basically for every input, there's one unique output. And you may have learned about something called the vertical line test, which says that if a vertical line passes through a function at more than one point, it's not a function. So what do we see here? If I draw a vertical line, x equals 0.5, we can see it crosses at like basically infinite points. This is not a function. So in order to fix this, For every one input, we have one unique output. We restrict the bounds. And when we do arcsine of x, we can see we restrict the bounds to pi over 2 to negative pi over 2, because this small section has all of the possible returning values, or all the possible values for sine x, all the way from negative pi over 2 to pi over 2. Now let's look at that exact same thing, but for arc cos of x. Kind of zoomed out here. For arc cos of x, you can see it goes from 0 to pi. So let's actually write this down. The domain of arc sine of x is from negative pi over 2 is less than equal to x is less than equal to pi over 2. All right. Arc cos of x is going to be from here 0 to pi. 0 is less than x is less than equal to pi. And finally, we have our arc tan of x. And that's going to be from, let's graph it, arc tan x. So we have an asymptote here, because you remember the tan function looks kind of crazy. That. We have an asymptote here as we flip this over. And as we get closer and closer to infinity, you're going to notice it's going to reach negative pi over 2 is less than or equal to x is less than or equal to pi over 2. Okay, so this is pretty cool. We can put in any of these angles as long as it's in between this domain, and it'll give us back the corresponding ratio for that corresponding function. That's cool. And we know how to solve something like sine of the sine inverse of x. This is just x. But what if we had a composition of functions? What if we had something like, um, what if we had something like, trace this, sine of cos inverse of x? What would this be? Whenever you see a composition of functions like this, multiple functions stacked onto each other, I want you to go back to your right angle triangle. Draw that out. So here, what are they telling us? They're telling us we have like an angle theta here, and this is a ratio. Remember? They're basically telling us that since this is cosine, we know that cosine is adjacent over a hypotenuse. Since this is the inverse cosine, it's going to be taking in this ratio, and it's going to be giving us back that angle, right? Oh, and sorry, I messed up. Back here, we put in any ratio, and it'll give us back the angle in this range. Yes. So now we know that cosine is adjacent over hypotenuse. So they're basically just telling us that the adjacent over hypotenuse is equal to x here. So to simplify this, let's just make our hypotenuse 1. What does that make the adjacent? It's going to be x. So our adjacent is here, and the hypotenuse is here. Now let's figure out what this other side would be. We can use the Pythagorean theorem here. It would be 1 minus x squared, the whole thing, root over. So that's what this side is going to be. Now we can figure out what the cosine of theta would be, because we know that this entire thing would return theta. So now we know that, so now we can figure out what sine theta is. Sine theta is just the opposite over the hypotenuse. So we know that the opposite here is this thing that we just found, and we know the hypotenuse is 1. So this thing is just going to equal the square root of 1 minus x squared divided by 1, or just the square root of 1 minus x squared. So whenever you see a composition of functions like this, go back to your triangle, solve for all of the sides, and then from there you'll be able to substitute it back in. Just remember, the inverse trigonometric functions will take in the ratio and give you back the angle, and the normal trigonometric functions will take in the angle and give you back the ratio. Now we know what inverse trigonometric functions are and how we can solve with a composition of functions, we're actually ready to start using or solving linear trigonometric equations. So what's linear? It's just going to be to the power of 1. So no sine squareds, cos squareds, anything like that, just 1. So say we have 2 sine x plus 3 equals -4. These are just some arbitrary numbers. This implies that we can, first we gotta isolate the sine x, just like you manipulate anything algebraically. Take 3 to this side, divide by 2. 4 minus 3 is -7, and then divide that by 2. And now we know how to solve this as well. X is just going to be, gotta apply the inverse trigonometric function. And you can punch that into a calculator to figure that out. What if inside our argument we had something else? What if we had sine 2x, for example? 2x plus 1 equals uh, like 1. So what we're going to do here is basically we're just going to apply straight away here the inverse trigonometric function. If you had like a 2 out here, for example, you'd of course fix that. Isolate your trigonometric function first. Always your first step is going to be isolating the trigonometric function. And now you're going to apply your inverse trigonometric function. So we have 2x plus 1 equals sine inverse of 1/2. And you can use a calculator to figure that out. Calculator, calc. And then from here, we can just solve for x as we would any other algebraic equation. We have x equals sine inverse of 1/2, and then minus 1 divided by 2. And it's that simple, and you just punch that into your calculator to figure out whatever the value of x was. So whenever you're solving a linear trigonometric equation, what you're going to want to do is first isolate the trigonometric function. Once you've isolated the trigonometric function, you're just going to solve for the variable as you normally would. Now, there is just one more thing to mention when solving your trigonometric equations, and that's going to be basically, so say we had like, sine of pi, right? And we're switching to radians here because that's what you're going to need for pre-calculus. Say you had sine of pi. Whip out your unit circle here. Pi over 2 is over here, so this is going to be pi. So sine of pi is 0, right? But what if we added 2 pi to that? Sine of 3 pi. Well, you have pi here, 2 pi, 3 pi, all the way back here. It's going to be the exact same answer. And it's going to be the same because the entire circle is 2 pi. As long as you add 2 pi to your answer, it's always going to be the same. So you could say that sine of pi equals sine of 3 pi. Or, in other words, this equals sine of pi plus 2 pi, right? And if you want to generalize this even further, you could say for any trigonometric function, doesn't matter if it's sine or cos, but sine of x is going to equal sine of x plus 2 pi. So now let's go back up to what we were talking about here when we solved this trigonometric equation. Since x, what is it? It's an angle. And if we add 2 pi to this angle, we're basically just going to get, the same answer back. So when you solve these things, you're going to want to add a 2 pi n. And all this n stands for is it's just an integer. So if you go around, if you add 2 pi to this, go around the circle, you end up in exactly the same place. An integer number of times, doesn't matter how many times you go around the circle, as long as you go around it exactly once each time, you're coming back to the same place. So every time you solve a trigonometric equation and use the inverse trigonometric function to get an angle, you're just going to add this onto it because it's the exact same thing. And it's the equation holds true at any of these points. Right, now that we've conquered the inverse or the linear trigonometric equations, let's move on to quadratics. So you already know how to solve a quadratic, right? If you have ax squared plus bx plus c, this is just going to be equal to use the quadratic equation minus b plus minus the square root of b squared minus 4ac divided by 2a. You can just use the quadratic equation here, and it's going to be the exact same thing if you see something like, sine squared x. All right, sine squared x plus, sine x. First of all, if there's no c, what you're just going to do is you're going to take a sine x out, pull it out here, and you're left with sine x plus 1. And if this equals 0, don't make the mistake of just canceling a sine x out, because then you're just left with, this sine x plus 1, and you're going to start solving for that. And yeah, you're going to have one correct solution, but you're going to miss out on this other correct solution. Because the truth is, if this is 0 or this is 0, since we're multiplying them together, both of them can lead to the correct answer. So just like with our normal quadratics, every trigonometric quadratic equation is going to have two solutions. So we got to solve for each of them separate. Sine of x equals 0 and sine of x plus 1 equals 0. And now that you know how to solve linear equations, you should be able to do this pretty easily using your inverse trig. Now, what if I have something like sine squared of x plus cosine of x equals 0? How am I supposed to switch in between these two? Well, this is where our handy Pythagorean identities are going to come into play. Let's go back to our unit circle real quick. What is any point on here? We know that x is going to be cos of x, cosine of x, and we know the y is going to be sine of x. And what's the distance here? The distance from the origin to the length of this line, from the origin all the way up to this point over here. It's just going to be the radius of our circle. And since it's a unit circle, that's just going to be 1, because that's the unit circle. All right, now how do we find distance? Well, distance is just going to be the square root of the x squared, cosine squared of x, that's the x here, plus the y squared, sine squared of x. And that's, again, basically just the Pythagorean theorem. We're just using the base here, the height here, and we're using the Pythagorean theorem, a squared plus b squared equals c squared, to find the height, which is just going to be 1 squared. Or, sorry, not 1 squared, it's just going to be 1. Now from here, we can take the square of both sides, and we get cosine squared x plus sine squared x equals 1, because 1 squared is just 1. All right, and this is our main Pythagorean identity. Now, let's say we were to divide both of everything by cosine of x. Cosine squared of x. Cosine squared of x divided by cosine squared of x is 1 plus sine squared of x over cosine squared of x. And this equals 1 over cosine squared of x. Now this is equal to 1 plus, we can take this squared out, and we get sine of x divided by cosine of x whole squared. And what's this thing equal to? Well, sine of x divided by cosine of x, that's just tan. So we have 1 plus tan squared of x equals, and 1 over cosine squared of x is just going to be secant x. So that's secant squared x. And then finally, we have just one more. If we divide by sine of x, we get, in a similar way, cot squared x, cotangent, plus 1 equals cosecant squared of x. So these three are our main Pythagorean identities, are our Pythagorean identities. And now let's see if we can apply this into this problem we were trying to solve earlier. So we know that sine squared of x is just going to be, if we move the cosine to this side, we know that the sine squared is just going to be 1 minus cosine squared. So let's substitute that in here. I'll just rewrite the problem down here. We have sine squared of x plus cosine of x equals 0. Use your Pythagorean identity. Cos squared of x plus sine squared of x equals 1, which implies that sine squared of x equals 1 minus cosine squared of x. So this implies, just substitute that in here, and we get 1 minus cosine squared of x plus cosine of x equals 0. And now this is just your standard quadratic equation, and you can solve this just like you'd solve any other quadratic equation, either using, the quadratic theorem, minus b plus minus whatever, or you could also try factoring it out. One more thing is, if this is hard for you conceptually, just try to use some other variable, u, and say u equals cosine of x. Now substitute that back into here. The 1 is going to remain 1, minus cosine of x. Well, we know cosine is u, so this would be minus u squared, plus u. And then this entire thing just equals 0. Now from here, when we solve for u, just multiply everything by a negative 1, minus u minus 1 equals 0. And we can probably try to factor from here. No, I'm not seeing anything. So you're just going to use the, quadratic formula here. And it's going to be, minus b, or here b is 1 plus minus square root of 1 minus 4ac plus 5 divided by 2a. And you're going to get this thing right here. And you know that u equals this, which implies that cosine of x equals the exact same thing because we said u equals the cosine of x, square root of 6 divided by 2. And from here, you can apply the arc sine onto both of these solutions, and you'll get the exact same answer. So just conceptually, whichever one works better for you, you can use that. At this point, we know a rather sizable number of identities, and we can start proving trigonometric. Um, we can start proving other trigonometric identities. A trigonometric identity is basically just something like they're going to ask you, prove that 2x plus 3 equals 2x plus 6, but it's probably going to be a little more difficult and not quite as straightforward. So from here, all you got to do is just take the left-hand side and take the right-hand side separately. Make sure you take them separately, and you have to make sure you come to the exact same, numbers. So you get 2x plus 6 here, and you have 2x plus 6 here, and we can see that these both equal each other, which means the identity is proved. Nice. But the thing is, uh, a mistake I'll often see is they'll try to combine both of these. Um, and students will treat it as if it's like one equation. But it's really important here to split them up, consider them both separately, and try to get to the same answer independently. Like get the same number on both of the sides independently from each other. As a general rule of thumb, whenever you're solving these types of uh, identities, is to first of all use your Pythagorean identities, use your even odd identities, use your reciprocal identities, use your quotient identities, use all of the identities you know. And from there, you're basically just first of all going to want to simplify. Cancel out anything that's like, really, really, uh, um, that's easy to cancel out on both sides. So I have like a 2 here. I could cancel that out on both sides. And then from there, you're gonna want to, if you still haven't proved it yet, you're gonna want to convert everything into cosines and sines. Get as basic as possible. And after you follow those two steps, simplifying and then converting down to cosines and sines, you should be able to solve um, most of these identities pretty easily. And the final step in our analytic trigonometry journey is just going to be a handful of more formulas that you're going to be able to use to um, solve even more identities and solve even more equations. So first up, we have cosine A plus B equals cosine A cosine B minus sine A sine B. There is a very rigorous proof for this. I mean, it's not that rigorous, but I'm not going to prove it here. And then to get cosine A minus B, you're simply just going to substitute in a minus B for this plus B here. In fact, you don't even need this formula. These are basically the exact same thing. Just substitute in a negative number here and you'll be fine. Exact same thing for sine, not the exact same formula, but it's going to be sine A cosine B plus cosine A sine B. And the minus formula isn't really like necessary. You just need to know this plus formula, substitute a negative number for this. And then finally, we have tan A plus B. This is, you get this from dividing the sine formula by the cos formula. And you'll get tan A plus tan B divided by 1 minus tan A times tan B. And again, if you want the minus version, you can just substitute in minus B. Okay, now we're going to have the two, the double angle formulas. So the double angle formulas are essentially just when you take like when you take an A and B here, I know it's alpha and beta, but when you take an A and B here, if you just substitute A both times, so I have cos A times cos A here, just ignore the B, pretend it's an A, because they have the same value. So we have cos A times cos A here, that's cos squared A. You can see that's where this cos squared theta is coming from. And we have sine A times sine A again. And that's going to be, sine squared theta. And that's where that's coming from down here. So if you just substitute in the same value for this formula, you'll get these formulas, which are the double angle formulas. You can use those to simplify from 2 theta down to just terms of theta. And also if you had something like, sine of 75 degrees, we couldn't solve that before, but now using this formula, we know that this is just sine of 15 plus, 60. So you go back up here and and you can apply this formula here, just up there, plug that into a calculator, boom. Or you don't even need a calculator for this anymore because you know what the values of sine 15 and sine 60 are, and that's all you have up here. And the values of cos 15 and cos 60, all in degrees, by the way. Okay, so now let's move on to the power reduction formulas. The power reduction formulas are derived from this equation right here, the second one, or at least for sine it is. You're going to have cos, cos 2 theta equals 1 minus 2 sine squared theta, which implies solve for sine squared theta, and you get sine theta equals, or you get sine squared theta equals, so you bring it to this side, you bring cos theta to this side, and you have 1 minus cos 2 theta, and we also had a 2 here, just going to divide by 2, and we get this. So you can see we went from a second power down to just a first power, but we did increase the value on the theta. In a similar way, you can prove this formula right here using this and using this double angle formula and solving for cos squared theta, and then you just divide both of them and you get the tan squared theta, which should be pretty obvious. And then finally, we have our half angle formulas. So our half angle formulas are derived from these power reducing formulas. First let's start with sine squared theta equals 1 minus cos 2 theta divided by 2. So now let's substitute, let's say that, theta equals alpha by 2, or let's just say a by 2. So now we have sine squared a by 2 equals 1 minus cos times 2, and then theta is a by 2. This 2 comes down here, divided by 2, which, just equals 1 minus cos theta divided by 2. Now, if we apply the square root, we get that this implies that sine theta, or sine alpha by 2, or a by 2, equals the square root of this entire thing, which is just going to be 1 minus cosine theta divided by 2. And that's how you get your half angle formula. Oh, and of course we're taking square root, so you got to keep a plus minus. That's how you get your half angle formula right here, right over there. And a similar way you can prove the cosine one and the tan theta, you just divide it. So these are all of the, identities you have to keep in mind. You got to memorize all of these. And using these, you're going to be able to solve the trigonometric identities and the trigonometric equations. Hope this helps.